Bismillah ar-Rahman ar-Rahim. This video is about minimum mean squared error estimation. So we have a vector y, which is k-dimensional. So vector y has k components. Those are the observations or measurements. So we know the components of vector y. Using those components, we want to estimate vector x. Vector x is n-dimensional. So we have x1, x2, all the way to xn. Those are n random variables in random vector x. The task is to build an estimator for x. And this estimator is a vector of the same size, so it is n-dimensional. I will call it vector g of y. The estimates will depend on the components of vector y, which are assumed to be known. G of y will have n elements. The first one is g1 of y1 to yk. That's our first function, g1. And given y1 to yk, g1 produces a number. This number will be our estimate for x1. g2 of y1 to yk is our estimate for x2, and so on. The question is, how do we obtain those functions? How do we construct the estimators? In MMSE, we obtain the g's such that the mean squared error is minimized. So what is the mean squared error? We have a vector x minus g of y. This is the vector of estimation errors. The first component in this vector is x1 minus g1 of y1 to yk. x1 is the random variable or parameter to be estimated. g1 of the y's is the estimate. The difference, the discrepancy between x1 and g1 is the estimation error. The jth element in this vector is the estimation error in estimating random variable xj. It is xj minus gj of y1 to yk. And this is the estimate for xj, and the difference is the estimation error. What we do is that we compute the L2 norm squared of this vector. And the L2 norm squared is summation j from 1 to n, xj minus gj of y1 to yk squared. That's the L2 norm squared. Now, what is the mean squared error? The mean squared error is to take the expectation of this L2 norm squared. And it is conditional expectation because we have the observations or measurements. Those are known. And based on them, we are finding estimates for the components of vector x. So this is given y. This is the mean squared error given y. The idea of MMSE is to obtain the estimators, those functions, g1, g2, all the way to gn, such that this mean squared error given y is minimized. So we have a claim, and this claim is that the minimizer is the expectation of x given y. So this is an n-dimensional vector, and the first component is the expectation of x1 given y1 to yk. The second component is expectation x2 given y1 to yk, and so forth. So we have n conditional expectations. The jth element here is the conditional expectation of xj given the y's, given the measurements. So this is a vector of conditional expectations, and each one of them is the estimate of the respective element in vector x, such that the mean squared error given y is minimized. To show that this is really the best estimate in the sense of minimizing the mean squared error, let's take this expectation. So this is the mean squared error given y. Now what we do is that we add and subtract this n-dimensional vector, the conditional expectation of x given y. So I will have here x minus expectation of x given y, then plus expectation of x given y, then minus g of y. Let's expand the L2 norm squared, treating these two terms as a vector and these two terms as a vector. So we get three terms. The first one is the conditional expectation given y of the L2 norm squared of x minus expectation of x given y. The second term will be the conditional expectation given y. Now we have the L2 norm squared of expectation of x given y minus g of y. Then we have the cross term, which is to expectation of x given y minus g of y transpose times x minus the expectation of x given y. So what we have here on the left-hand side is the mean squared error given y if we use the g functions as estimators, g1, g2, all the way to gn. On the other side, we have three terms. The first one of them is the mean squared error given y if for our estimators we use the conditional expectations, of the components of vector x given y1 to yk, if we use this vector as our vector of estimates. We have two more terms. Let's focus on this one here. Now, expectation of x given y is a function of y. G of y is a function of y. And so when we do the expectation given y, those vectors, they contain constants. So this expectation here is 2. And so this can be taken outside. And then we apply the expectation here to this x minus expectation of x given y. But what is this? So here, let's copy this. This one is expectation of x given y minus, when we take the expectation, this is like a constant vector because it's a function of y. So the expectation given y is just itself. And this difference is basically the all zero vector in n-dimensional space. And the inner product between any vector and the all zero vector is 0. So this third term is interesting. This third term is simply equal to 0. The second term, the most important thing, is that it is the expectation of the L2 norm squared. So this is a quantity that is greater than or equal to 0. So the mean squared error given y, if we use the g's as estimators, is the mean squared error if we use expectation of x given y as the vector of estimators plus a non-negative quantity. So the conclusion is that for every g, we have the expectation of the L2 norm squared of x minus gy, and this expectation is given y. This is greater than or equal to the expectation, or the conditional expectation given y, of the L2 norm squared of x minus the expectation of x given y. So if we want to find the estimators, the functions of the observations that minimize the mean squared error, then they are the components of this vector. Remember that the jth component in this vector is the conditional expectation of xj given y1 to yk. This will be our estimate for xj. And this vector of estimators will be the vector that achieves the minimum mean squared error. Now, what about uniqueness? Is there like another vector that can achieve the minimum mean squared error? So let's investigate uniqueness. Suppose that the mean squared error is minimized by x1 hat. So that's a minimizer of the mean squared error, and x2 hat. Each one of those vectors is n-dimensional, contains functions of the observations that provide estimates for the components of vector x. Suppose that the mean squared error is minimized by x1 hat and also by x2 hat. Let the minimum mean squared error be d squared. So this means that the expectation of the L2 norm squared of x minus x1 hat given y, if we take the square root, this is d, and also this is the conditional expectation given y of the L2 norm squared of x minus x2 hat. Consider the estimator x1 hat plus x2 hat over 2. So let's basically make our estimate for vector x be the average of these two vectors. Now we know that the minimum mean squared error is d squared. So this means that d is less than or equal to the conditional expectation given y raised to the power 1/2 of the L2 norm squared of x minus x1 hat plus x2 hat divided by 2. Why is this? Because here we are using this vector as an estimator, and among all estimators, x1 hat and x2 hat provide the minimum mean squared error, which is d squared. So if we take the square root, it's d. Let's take this 1/2 as a common factor. So if we take it as a common factor, it gets outside the L2 norm squared as 1/4. But then we have 1/2 here, so it will get outside as 1/2. Then we have expectation to the 1/2 given y, and after taking this as a common factor, we will have 2x let's write the L2 norm squared in this form: x minus x1 hat plus x minus x2 hat. Now we have Minkowski. So let's apply it. So let's apply the Minkowski's inequality. So it tells us that the expectation of the L2 norm squared of a plus p to the 1/2, this is less than or equal to the expectation of the L2 norm squared of a to the 1/2 plus the expectation of the L2 norm squared of b to the 1/2. Applying this here, we have an upper bound on this expectation as 1/2, which is this 1/2 expectation of the L2 norm squared of x minus x1 hat, and this expectation is given y. And there is a similar term, but rather than using x1 hat, we have x2 hat. Now each one of those is equal to d. So this is half d plus half d. That's d. So we have a chain, and it starts here with d, and we end here with d. It means that this expectation is equal to d, which means that x1 hat plus x2 hat divided by 2 is optimal. It also achieves the minimum of the mean squared error. Is equal. Now let's investigate the L2 norm squared of x1 hat minus x2 hat. Now this is double the L2 norm squared of x minus x1 hat plus double the L2 norm squared of x minus x2 hat minus 4 times the L2 norm squared of x minus x1 hat plus x2 hat divided by 2. And this can be verified, this identity here can be verified by simply expanding the right-hand side. So here, what do we have here? We have, because we have a 2, we have 2, the L2 norm squared of x, plus 2, the L2 norm squared of x1 hat, and then we have minus 4, x transpose x1 hat. What do we have from here? We have 2, the L2 norm squared of x, plus 2, the L2 norm squared of x2 hat, and then we have minus 4, x transpose x2 hat. And from here, we have minus 4, the L2 norm squared of x. Then we have minus the L2 norm squared of x1 hat plus x2 hat. And finally, we have plus 4 x transpose times x1 hat plus x2 hat. Those guys cancel. Those guys cancel. And then if we expand this one, it gives us minus the L2 norm squared of x1 hat minus the L2 norm squared of x2 hat. And then we have minus 2 x1 hat transpose x2 hat. We have here 2 times the L2 norm squared of x1 hat. And so the final result will be the L2 norm squared of x1 hat. Similarly, we have the L2 norm squared of x2 hat. And then we have minus 2x1 hat transpose x2 hat. And this is exactly the L2 norm squared of the difference. Now, take expectation of both sides given y. Here we have expectation given y, expectation given y, expectation given y. What is this? This is the minimum mean squared error. That's d squared. This is also d squared. And this one, we have just shown that it is d squared. So this is equal to 0. The expectation given y of this L2 norm squared of the difference between x1 hat and x2 hat is 0. Now let's study the probability of the event that the L2 norm squared of x1 hat minus x2 hat is strictly positive given y. This is equal to the probability that union k is a positive integer. If something is strictly positive, this is equivalent to the L2 norm squared being greater than or equal to 1 over k. If the L2 norm squared is greater than or equal to 1 over some positive integer, then it is positive. And if the L2 norm squared is strictly positive, then there must be some integer, say m, such that the L2 norm squared is greater than or equal to 1 over m. Now, by the continuity of probability, so we have continuity. This is the limit as k tends to infinity of the probability that the L2 norm squared is greater than or equal to 1 over k given y. Now, apply Markov's inequality. So here we have Markov. So this will be limit k tends to infinity. Then we have this expectation of the L2 norm squared given y. Then we need to divide by 1 over k. But what is this expectation? We have just shown that this expectation is exactly equal to 0. So this is the limit as k tends to infinity of k times 0. This is the limit as k tends to infinity of the all 0 sequence. And this is 0. So the probability that the L2 norm squared is strictly positive is equal to 0. Well, the L2 norm squared is a non-negative quantity. So this means that the probability of this L2 norm squared being equal to 0, this is equal to 1, which means that given the vector of measurements or observations y, we have that this L2 norm squared is equal to 0 almost surely with probability 1. And from the properties of norms, we know that if the norm is equal to 0, then basically whatever we have inside, the vector inside must be the all 0 vector. So we have x1 hat is equal to x2 hat with probability 1. So if there are two estimators minimizing the mean squared error, then they are equal with probability 1. So this is the question of uniqueness. The last thing, what is the minimum mean squared error averaged over y, the vector of observations? Well, this will be the expectation of the L2 norm squared of x minus the expectation of x given y. We know that this vector, the conditional expectation of x given y, is the minimizer of the mean squared error. We can write down this expectation using iterated expectations. So this is an outer expectation given y, and then we have the conditional mean squared error inside. So this will be expectation of the L2 norm squared of x minus the expectation of x given y, like this. So here we use the conditional distribution of x given y. Now, this is the expression for the average mean squared error when we use the conditional expectation of x given y as our estimator. Sometimes it is written in a particular way, which basically is we take this L2 norm squared and write it as an inner product of two vectors. So I take this L2 norm squared and write it as x minus the expectation of x given y transpose x minus expectation of x given y. Now, this is a scalar. This is a 1-by-1 matrix. So this is equal to the trace of the same quantity. So again, it is a scalar, yes. Think of it as a 1-by-1 matrix. So it is a matrix with just one element on the main diagonal. And so if you take its trace, it is just this element. Okay, so we'll do this. We'll write down this inner product as trace. The trick here is that if we have a matrix A of size small m by small n and matrix B of size small n by small m, then the trace of AB is equal to the trace of BA. So this is the trick that we will use here. We will convert the inner product into an outer product by swapping the row vector and the column vector. So this is expectation over vector y of, I have expectation. This inner expectation is x given y. Then I will write this trace. We will write the column vector first, and then the row vector, which is the transpose of the column vector. Now this is an n by n matrix. We have an outer product. Expectation of the trace is the trace of expectations, and this is due to the linearity of the expectation operator. So suppose that we have a matrix with random variables a, b, c, d. Now, what will happen if we take expectation and then we take trace? An expectation applied to a random matrix, it just means that we apply the expectation component twice, element twice. So after applying the expectation, our matrix will be expectation of A, expectation of B, expectation of C, expectation of D. Now, when we take the trace of this matrix, we sum the elements on the main diagonal. Those are the expectation of A plus the expectation of D. What about expectation of the trace? In this case, we compute the trace first, and the trace is A plus D. Then we take expectation, but expectation is linear. By the linearity of expectation, this is also expectation A plus expectation D. So this is a demonstration that we can swap expectation and trace. So this is expectation over the y's, and then we have the trace, okay, and then we have the expectation of this outer product, so x minus expectation x given y times x minus expectation of x given y transpose. This is given y. Now, what is this expectation here? This is the expectation of the outer product that we use to compute the covariance matrix or the autocovariance matrix of a random vector. So this is exactly what we have here. We have the matrix CXX given Y. So this is the expression that we wanted to derive. We compute the trace of this covariance matrix, and then this will be a function of the observations Y. We take the expectation finally with respect to the components of vector Y from Y1 to Y big K. this covariance matrix of vector x. It is the conditional covariance matrix or auto covariance matrix given y. So element VL in this matrix is its covariance matrix. So we need to take xv and then we need to subtract its mean. But since this is conditional covariance, we subtract the mean value of xv given the y's from y1 to yk. Then we do the same to xl. We subtract the conditional mean of xl given the y's from y1 to yk. And then we multiply these guys and take the expectation given y1 to yk. So this is element VL in this matrix.